Hi, in this video, we want to take a look at using scatterplots to transform our data and build better models. All right, so we're in the situation where the models should have non-degree one terms. And now the standard out of the box linear regression method is always to have degree one terms. So that's just the variable itself. When I say degree one, think of that as like a polynomial. Degree two is where it's squared. Well, degree zero is the intercept. And so here, what we want to do, we want to use the scatter plots to kind of infer what we should be including, what we should be excluding from our model. All right, so here, just loading the data like usual. And like I've done in the past, I'm going to go ahead and I'm going to sort the data by the target variable. And then I'm going to change the row names so that it corresponds to it has a perfect Spearman correlation with the target variable. Why do I do this? Because on the plots, when it starts giving the row names on the plots, the diagnostic plots in particular, I can see, hey, these are all big numbers, they're all small numbers in the middle. It gives me additional information so I can spot a pattern that might not be obvious otherwise. Now, the next thing I want to do, I'm going to color the points. And so I'm just going through and I'm making sure that the color gradient corresponds to the target variable. This way, I might be able to spot something. On this particular problem, these two steps don't actually help, but it's good practice. I feel like you should always do this. So I'm doing it here also. All right, now let's look at the pairs plot. Now this is going to be like a critical step for this video presentation, and this is the one that we really want to key in on. All right, so I've got my target variable. I've got two predictor variables. Okay, so a lot of stuff going on. So basically how I like to proceed, start with a target variable and then move down, lower. Okay, so here I see I've got the target variable, and here I'm using the x-axis is the first predictor variable, and it looks like there's a functional relationship between it, nearly functional relationship. So when I say functional relationship, I'm saying that there's no statistical variation, no error in measurement, anything like that in the data. It's not quite that way, but it's close. So I know that I could probably get a pretty good model out of X1 if I take the time to do this. All right. Now when I move over here, I can see that when I say functional relationship, that means a function as in college algebra function, vertical line only crosses once. Here, I can see that there's definitely a relationship going on, but it's not as clear what the relationship between X2 and Y is. So like if I have this value of X2, either I want this value or that value, it's not 100% certain which value I actually want. So I'm not feeling as good about the second predictor variable as the first, but there's definitely a relationship in there. And my job as a data analyst, as a statistician, is to find that relationship if that's the best way to go. Now I come down here, I'm looking at the predictor variables, and I can clearly see that there's an S-bend here. But this does not define a function, right? But if I come down here, look at that, look at that. If I say that X2 depends on X1, I can see that I have what looks to be a function. Now it's not exactly a function because of there's a little bit of variation in the data if I was to actually zoom in on the scatter plot, but there's something going on here. And so remember that these two plots are reflections of each other over the line y equals x. And these two are reflections. These two are reflections. So, I don't really, like this version of it doesn't really help me any. And here, this is even more confusing. And I'm in the situation where y needs to be the dependent variable. So these plots really aren't that helpful for me anyway, because in this format, we're presenting it as y is the predictor variable, which it's not. We know it's not. All right, so when I look at the scatter plots, I can see that it looks like y depends on x1 and x2 depends on x1. All right, so what I chose to do when I started looking at this data, I started working on the two predictor variables first. Why? Because this looks like a simpler relationship. This looks like some kind of sine wave to me right off the bat. This looks like a sine wave with maybe a degree 1 term. Maybe, I'm not 100% sure. It might be a little bit more exotic, but this one's gonna be a little bit more complicated. So I'm gonna start here. And if I can figure out what's going on between these two, that might help me infer something about x1 and y. So I'm gonna go ahead and jump here. So this is gonna end up, when I'm all done, I'm not gonna end up using x2. I'm just kind of doing this to help me figure out like what I'm doing to understand the situation as a whole, ultimately. All right, so let's go ahead and let's look at the scatter plot. All right, so when I look here, all right, so I've got a peak down here and a peak down here. Okay, valley, it's more of a valley, not peak. But I can see that it goes from, about negative 1.5 to 1.5. And, so that looks kind of like, the standard sine wave. And I can see that it's going from, about -3 to 3. So if I say pi over 2, negative pi, and pi, this looks a lot like a sine wave to me. So let's go ahead and let's do this. All right, so what I did, if I have a sine wave relationship, then it's going to look very similar to the power series expansion of sine. And so I went ahead and started doing that. Now, if you remember sine from trigonometry, that's an odd function. As an odd function, I don't need any even terms. I don't need an intercept. I don't need a degree 2 term. I don't need a degree 4 term. I don't need a degree 8 term. Automatically, all even degree terms of x1, I don't need. So if you look through here, you'll notice that I will go x2 depends on no intercept, x1, that's degree 1 term, cube term, degree 3, to the 5th power, to the 7th power. Now, during model exploration, I found that this 7th degree term did not add to the model. Why is that? Because there's some variability in the data. It's not a perfect function relationship. So I went ahead and I said, hey, that looks like a good model formula for me to work with. And so on my next step, what I did, I built the model using this formula, and then I compared the coefficients to the power series expansion of sine. If it is a regular vanilla sine wave, these should be very close to each other. All right, so I go through and I build the model. I call it linear model x2 by x1. And then I do the summary so I can look at the coefficients. I can see that everything is statistically significant. And now here I've got 1, now negative 0.16, and then 0.006. Now, if you look at the power series expansion of sine, this is going to be 1 over 6, and then this is going to be 1 over 5 factorial. And so this is really close. So all three of these are close to the coefficients of the sine power series. Now, if they weren't, what I would start doing, I would have started doing some calculus. I would have assumed that there's a coefficient inside the, there's a coefficient of x1 inside the sine wave. I would take the power series expansion, and then I would start trying to do some arithmetic or some algebra to match up these coefficients to get it to work out. And then I would have had like a really, I get a really good model. When I go down here, look at how tight my R squared and my adjusted R squared are. I mean, that you are not going to get better than that. This is also fake generated data, so you can achieve something that's good. If I was to see in real life 0.95, I would be doing a backflip. I can't do backflips. But this is a really good fit. I'm very satisfied with this. When I looked at the 7th degree term, the 7th degree term was not statistically significant to improve the model, so I go ahead and dropped it when I ran ANOVA. Here's the ANOVA. Everything is looking good. So this is saying that having the degree 1 term is worth having, then adding the degree 3 term is worth adding, and then adding the degree 5 term to the prior 2 is worth doing. So that is good. All right, so now I'm getting a feel for how to work with these sine waves now. And let's go ahead and start looking at the target variable and the first predictor. So this one was a more complicated scatter plot. Okay, so when I look at it, let's see, where is it? I see that I have, when I go from here to here, horizontally, that's about 1.5. All right, so 1.5, that's close to pi over 2. So I'm looking at that, and I'm like, you know, that's, and if I look here, from negative pi over 2 to pi over 2, horizontal position, then I'm thinking this might have an angular distance of 2 because of the divide by 2 aspect. Okay, so now I'm looking at maybe a degree 1 term plus sine of 2x1, maybe? That's my feel at this point. Now I notice that also the peaks are around negative pi over 2 and pi over 2, and they're equal distance from the origin. So if I look back down on this, if I look at the plot, I notice that the horizontal position here to the origin and the horizontal position here to the origin are about the same. So I've got the added part is most at like equal amounts left and right. So that's leading me to believe that the sine wave is actually an even function. Okay, well, even function. Is sine an even function? No, it's an odd function. It's odd, just like me. I'm odd, right? I can hear you laughing through the internet. That's comedy gold right there. So I'm going to go with cosine. So I suspect that cosine of 2x1 is what I should have in my model. All right, so let's go ahead and do that. So here I go ahead and plot the points. So what I'm going to do, I see that there's kind of like an overall increasing aspect to that scatter plot. So I have the degree 1 term, and I'm going to try to have cosine of 2x in my model. And let's see if that fits very well. I'll be very happy. And we can see from the dark line that it fits the data points very, very well. Let's take a look at the summary and the ANOVA. All right, so all of these are statistically significant. This is looking really good. I see that I cannot ask for a better R squared, adjusted R squared. They're also close to each other, which indicates that that is consistent with me not overfitting. I look at the ANOVA. The ANOVA is looking good, so I'm feeling really good about this. Now, what would I have done if this didn't work out? Okay, so I still believe that this is an even function. So that means that I'm looking towards using cosine in some way, shape, or form. What I would have tried doing next, if this didn't work out, I would have honestly started working with even polynomial terms on x1 and to take a look at how it compares to the power series of cosine. And if it ended up looking pretty close to certain values, like on like a different angular frequency, then I would have worked with that. And if that didn't work out, then I would have started working on more exotic terms. Okay, well, let's look at the diagnostic plots. So there's a good lesson in the diagnostic plots here. So first thing I want you to do, I want you to take a good hard look at the output of the summary statement. All right, this everything is statistically significant within machine accuracy. So that's consistent with things being good. I have super tiny standard error on my coefficients. My t-values are huge. I've got nearly perfect R-squared, adjusted R-squared. My F-test, super, super huge F-statistic. So like everything is pointing to this being a good, solid model. And the ANOVA test does the same thing. Everything looks really, really good. I'm really pumped up about this. Now, what I'm going to do at this point, I'm going to start looking at the residuals. Now, let's check this out. That's greater than 4. That's, that's about like -4 for the residual. And like, oh no, it's 4, it's huge, because it's approximately normal distribution scale. But think about it. My residuals were super, super tight. I have a really tight fitting model. Does it matter? Does this point matter? Well, honestly, since I have such a good fit, my residuals and magnitude don't matter. I've standardized, so when I standardize, something's going to be greater than 3. Something's going to be less than -3. So something is going to be going on when I do the standardized residuals. But I have such a tight model, honestly, I don't even care about my residuals. But if I just jumped to here and started looking at it without considering the magnitude of it, these residuals are not operationally significant, so I don't care. All right, so let's look at the next one. All right, here's standardized residuals on X2. Let's check it with respect to the fitted values. All right, maybe non-standard variance. But still, this is so small that, remember, something's going to be poking out when I standardize. All right, pretty much the same story. Now, a good plot to always run is to plot your observed values versus your fitted values. This is a good way to double check. Do I have a good model? And then plot the line with y equals x on there. Let's take a look. Does that look like a straight line? Does it look like the points are adhering to that red line? Yes, it does. Is it perfect? No. That's why we're doing statistics. All right, let's look at our diagnostic plots. All right, so something about this is that the diagnostic plots are always going to label the 3 biggest. That by default, R will always label the three most extreme cases. Well, the residuals are so small that it doesn't even really matter. Like I'm not worried about this. Something is going to be the biggest. There's going to be a biggest 3. It's going to get labeled. All right, it's probably not normal, but it's so tight, it's not going to be an issue. My neighbor's landscaper is working. I hope you don't hear it. All right, well, that's all I got for you. Take care and goodbye.